Welcome back, it's me Tutor Binod. In this video we are going to talk about the indices. Let me first introduce by an example. Let us say we have 2 to the power 10. In this expression 2 is known as the base, whereas 10 is known as the power of 2, or also known as index of 2. So when we talk the plural form of index, it becomes indices. So when you deal with the base raised to the certain power, then we talk about indices. If we want to add 2 plus 2 plus 2 plus 2 plus 2 5 times, then we would be getting 10, which can also be written as 2 times 5. But if you want to multiply 2 5 times 2, I mean to say 2 times 2 times 2 times 2 times 2, it's equivalent or equal to the 2 to the power 5 1. Also you can see this as this is 2 to the power 1, this is 1, this is 2 to the power 1, this is 2 to the power 1, and this is also 2 to the power 1. So when you add all the powers, we will get 1 plus 1 plus 1 plus 1 plus 1, which is 2 to the power 5, and which is equal to 32. So this is how we use the indices, or the property, one of the property of indices. Similarly, if you want to add x 5 times, you would get 5x. Similarly, if you want to multiply x times x times x times x times x, you would get x to the power 5, similar to this example we just did earlier. Now let me make you familiar with some of the laws regarding indices. The first one is product law, or if you want to multiply two things with same base but different exponent, same base but different index. Suppose in this case it will be x to the power a plus b. For example, if I have x to the power 2 times x to the power 3, I would have x to the power 2 plus 3. Similarly, if you want to divide the indices with the same base by another one, then we have a base as x on both cases. So you would do, if you want to do it in the numerator side, you would be having x to the power a, and you would be subtracting the power which is in the denominator. But the thing is, it has to be of the same base. Only the indices should be different, but the base has to be same, must be same. Or you can also do it 1 over x to the power b minus a as this one. It's also done as this. If we gonna write x to the power 1, we can also write it as 1 over x to the power minus 1. So these are equivalent. Similarly, the another one is, if you have base to the power something and raised to the power something, then your power or indices will be multiplied. So x to the power a times b. Suppose you have 2 to the power 3 to the power 6, then you would have 2 to the power 3 times 6, which is 2 to the power 18. Similarly, if anything is raised to the power 0, it's equivalent or it's equal to 1. Suppose if you have 2 to the power 0, it's 1. Anything to the power 0 is 1. Even if you have something like 3000 to the power 0, it's 1. Even if so. Now let's me go through the root form. Suppose you have root under 2, square root of 2, then you would have 2 to the power 1 by 2. Similarly, if you have the root, nth root, then you would have x 1 to the power 1 over n when you want to elaborate this. But if you have x to the power m over here, as I saw it over here, you would have x to the power m, but this, if you want to get rid of the nth square, you would be multiplying with 1 by n, so it would be m over n, as you can see here. So these are the different things you should remember to proceed further with dealing with the problems regarding indices. Now let us see an example. The first example tells us that we have to evaluate 25 over 16 raised to the power 1 over 2. So which is nothing but, let's see, here is 1 over 2. So if we're gonna write this base as in terms of something raised to the power 2, then we would cancel 2 and 2, then it would be easier for us to elaborate. So 25 is nothing but 5 to the power 2, whereas 16 is 4 to the power 2, and our power for both would be 1 over 2. In this case, we can write 5 over 4 to the power 2 times 1 over 2, because if a to the power b to the power c, we can write as a to the power b times c. Similarly, we have 5 over 4 to the power 2 to the power 1 over 2, so I can write 5 over 4 to the power 2 times 1 over 2. Now 2 and 2 is gone, so 5 over 4 to the power 1. Any base to the power 1 is base by itself, so it's 5 over 4. Now let's see this one. We have 8 over 27 raised to the power negative 1/3 times 81 over 16 raised to the power 1/4. So can I write 8 as 2 to the power 3, whereas 27 is 3 to the power 3, because 3 times 3 is 9, times 3 is 27. Similarly, 2 times 2 times 2 is 8. Can you please try it for 81 over 16? I hope you did. Let's see. 81 is nothing but it's 3 to the power 4, because 3 times 3 is 9, times 3 is 27, times 3 is 81. Similarly, 16 is 2 to the power 4, and we have the power 1 over 4 over here. Similarly, for this one, we have the power negative 1/3. Now what can we do? As we did in our previous example, we can write this as 2 over 3 whole to the power 3, because if we have a to the power n over b to the power n, we can write it as a over v whole power to the n. That's why it's 2 over 3 to the power 3, but we have another power to it. It's negative 1/3, so I can multiply that. Times, similarly, I can do the same thing for the second terms, 3 over 2 to the power 4, but I have to multiply this with 1 over 4, because 1 over 4 is given to us from the question. So this 3 and 3 is cancelled. Similarly, 4 and 4 is cancelled out. We would be having now 2 over 3 to the power negative 1. Similarly, we'd have 3 over 2 to the power positive 1, which is again 3 over 2. This is multiply over here. Since a to the power minus 1 is 1 over a, so I can write this as 1 over 2 by 3, which is eventually 3 over 2 times 3 over 2, which is 3 times 3 is 9 over 4. That's how we deal with this kind of indices problem. Now in this question we have 27 over 8 raised to the power 1/3, and the whole power is 2. So 27 is again 3 to the power 3, whereas 8 is 2 to the power 3 raised to the power 1/3, and again to the power 2. So this is 3 over 2. This power we can multiply, so 3 times 1 over 3, and this is gone, but this is raised to the power 2 altogether. Now 3 to the power 2 is 9, and 2 to the power 2 is 4. So this is our answer. That's how we do this problem. Now let us say another problem. This is relatively tougher. The first part is x to the power m, and the second terms on the numerator is x to the power m plus 1, and the base is also of the same base. I mean to say the denominator terms are also of the same base. So whenever we have the same base, we can get the common. So let us take x to the power m common from these two terms. Now what is remain on the first terms on the numerator side? just 1, yeah, because if you divide this first term by the common, you would get 1. X to the power m over x to the power m is 1. Similarly, if you're gonna divide x to the power m plus 1 with the common term, which is x to the power m, you would have x to the power m plus 1 minus m, which is x to the power 1, which is x by itself. So let me write x over here. The numerator side is done. Can you please do the denominator side? You can pause the video and try it. I hope you get it. Now let's see here. Similarly, I can take x to the power m common. If I take x to the power m, I would be ended up with x to the power 2, which is x square minus 1. So this is gone because x to the power m over x to the power m is 1. So can I take -1 common from the top side so that I can get x minus 1, because the lower term is x square minus 1, which is also x square minus 1 square, and which will give me x minus 1, x plus 1. So x minus 1, x plus 1. Here we go, x minus 1 and x minus 1 is gone. So I would be having -1 over x plus 2. So -1 over x plus 1. Now let me introduce you with the indices problem regarding roots. I have, first of all, if there is nothing, that means you have a square root. That means there is 2 over here. But if there is given 3 or anything or n, then it's nth square. So nth root, I mean to say nth root. So in this case, if you are given just the root, that means it's a square root. So whenever the square root is given to you, you would be doing 2 to the power 1 over 2. If there is 2 to the power n, you would be doing 2 to the power 1 over n. If you are given root over x, then you would be doing x to the power 1 over 2. If there is n, then you would do, instead of 1 over 2, you would do 1 over n. I hope you got it. So let's see through another example. The question number 7 is, so in terms of square root, we have cube root over here. So it would give us 2 to the power. If it was nothing, it would be 1 over 2, but if it is 3, it would be 1 over 3. If it is n, it would be 1 over n. Similarly, this will give you 8 to the power 1/3. But if you want to do it further, you would have 8 as 2 to the power 3, which is 8 1/3. So whenever there is power to the power, we can multiply the power, which is 3 times 1/3. This is gone, which is 2 by itself. That's how we do the problems regarding indices of roots. Now let us see a little bit tougher problem regarding root. The first thing is 2 to the power a square minus b square. Because this term, if you want to see it closer, you would be getting a minus b, a plus b. Similarly, this would be b minus c, b plus c. Similarly, this would be c minus a, c plus a. So, and also, if you have x to the power root nth of x, then you would be getting x to the power 1 over n. Similarly, in this case, it would be 2 to the power this times 1 over this term. First, let me write a square minus b square as a minus b, a plus b. So this is this thing. I just elaborate the formula of a square minus b square to get this one. I hope nobody has problem over here. Now, its nth root, I mean to say a plus bth root of this term. So I can write 1 over a plus b. So let me write like this. Similarly, the second term I can write as 2 to the power b minus c, b plus c, and 1 over b plus c, and the last term will be 2 to the power c minus a, c plus a, whole to the power 1 over c plus a, c plus a. So a plus b and a plus b is cancelled out. Similarly, b plus c and b plus c is cancelled out. Similarly, c plus a and c plus a is cancelled out, because anything to the power and to the power of that, then power is multiplied. If you want to multiply this with this, this with this, and this power with this, you're gonna cancel a plus b terms over here. Similarly, b plus c term over here and c plus a over here. Let me write the remaining term as it is. So I would be having 2 to the power a minus b times, on here we would be having 2 to the power b minus c. Similarly, on the last one we would be having 2 to the power c minus a. So let me remind you, if I have a to the power x times b to the power y times, I mean to say a to the power y times a to the power z, you would be having a to the power x plus y plus z. So in this case you would be having 2 to the power a minus b plus b minus c plus c minus a. I hope you get it. So negative a, positive a cancelled out, b cancel out, and c is gone. So which would be giving us 2 to the power 0. 2 to the power 0 is as 1. Now let us do our final problem regarding indices. In this problem we have the same base a on all the three terms over here, which is multiplied with each other, and we have certain power raised to the certain power. Let's see what we can get. The first step is, since the base is same in all the case, let me write the base as it is. So if you have a to the power x over a to the power y, you can also write as a to the power x minus y. So this would be a to the power x minus y raised to the power x square plus xy plus y square. Similarly, the second term would be a to the power y minus z raised to the power y square plus yz plus z square. Similarly, the third term would be a to the power z minus x raised to the power z square plus zx plus x square. Now if you see it over here, you would be having, because if you have a x to the power a to the power b, then the power would be multiplied. Similarly, we can multiply these two power over here. So a to the power x minus y x square plus xy plus y square. Similarly, the second term would be a to the power y minus z y square plus yz plus z square. Then the third term would be a to the power z minus x z square plus zx plus x square. Can you tell me, or can you write what does this mean? This means nothing but it's a x cube minus y cube. Similarly, this is a y cube minus z cube. Similarly, this is a to the power z cube minus y cube. Why is that so? Because a cube minus b cube is a minus b a square plus ab plus b square. Now I have all the same base raised to the certain powers, so I can add all the powers because I have the same base, a to the power x cube minus y cube. Then I can add this term, which would be y cube minus z cube. Similarly, I can add this term plus z cube minus y cube. My x cube will be cancelled out with, oh, I'm sorry, this is x cube. So x cube term is gone, g cube term is gone, and y cube is gone. So a raised to the power 0, anything raised to the power 0 is 1. So our answer is 1. I hope this video is useful for you to understand indices and problems regarding to it. Also, if you have not yet subscribed my channel Tutor Binod, you can subscribe my channel and hit the bell icon so that you won't miss any updates. I'd be bringing up further useful videos regarding mathematics and science in near future. Thank you.